start recording. So everybody, we started recording. I would like to remind everybody that this is going to YouTube later. If anybody has a problem with it or anything else, please let me know. Bird, I'm giving you the control. Let me know when to start the video and which.
Excellent. So welcome everyone to the Concur session on language theory. My name is Bernd Finkbeiner. I'll be chairing the session. We have two talks, adaptive synchronization of pushdown automata and decomposing permutation automata. So I guess Igor already explained the rules. So we have the Q&A system and the chat. So please go ahead and already write questions during the videos, and then we'll pick them up in the 5 minutes after each video. All right, I guess, Igor, we can get started with the first talk.
Hello. In this video, we will talk about our work on the adaptive synchronization problem for pushdown automata. This is work done by my co-author Balasubramaniam and me, Tejaswini. Let us consider the model of a pushdown automata that we all know and love. We have a set of states, an input alphabet, and a stack onto which we can push and pop elements. A token represents which state the pushdown automata is currently in. For instance, currently the token is at the bottom left state. The transitions between the states dictate how the state and the stack change upon giving a certain input.
Okay, but can you give me an example of how the transitions work?
Yes. For example, once we input a coin, the token moves to the bottom right state and then pushes a teacup onto the stack. From here, if we input a note, then the token moves up and a teacup is pushed again. At this moment, if we once again give a coin, then the teacup on the top gets popped out of the stack. In this way, the token keeps on moving between states, appropriately changing the stack content on the way. But one day, all the tokens in the pushdown automata in the world have become invisible. Your pushdown automata still works fine, but you no longer know which state the pushdown automata is currently in, because from your perspective, the token could be anywhere.
Oh, wow. But is there some good news at all then?
Yes, you can still control what inputs you can give, and more importantly, you can observe the changes happening to the stack as and when you give these inputs.
Okay, but what do you mean by this? Can you give me an example?
For instance, one possible scenario in this pushdown automata is that you give a note as an input and then observe that a coffee cup is pushed in the stack. This would mean that the token was either at state 2 or 4 before the input, because those are the only two states which are capable of pushing a coffee cup after a note is given. Hence, the token is now either at state 1 or state 3. Afterwards, let's say you input a coin and the coffee cup is popped out. Notice that this action is possible at any of the states. So this action only tells you that the token is where it was before. So you can now say the token is still either at state 1 or state 3.
Okay, so the setting is fine, but what do you want to achieve now in this setting?
What we want is a strategy of giving inputs to a pushdown automata so that after we play out this strategy, there is exactly one state where the token could be in.
Ah, I guess you mean in this case, something like the following, right? Initially, according to us, the token can be in any of the 4 states. Then let's say we decide to give a coin, and so one of two things could happen. Either a coffee cup or a teacup gets pushed onto the stack. If we observe that a teacup is the one getting pushed, then only one of these two transitions could have taken place, and we know that the token is now either at state 3 or state 4. Now we can give a note, and then once again, either a coffee cup or a teacup gets pushed. If a teacup gets pushed, then we know that the token is at state 4. On the other hand, let's say the coffee cup was pushed. Then the token is currently at state 3. Now, in order to synchronize the PDA to state 4, we can now give a note as input, and the token now moves to state 4. So far, so good. And we have synchronized the token to state 4. Alternatively, if at the first step, a coffee cup was pushed, then we first input 2 coins, one after the other, so that the token is somewhere in the set 3, 4. Then we are already at a position similar to the one before. And so we simply apply the same strategy that we used in that case.
Yes, we do precisely something like this for this automaton.
Okay, but here the input that I gave depended on how the stack changed in the previous steps. For instance, initially I gave a coin as input, and then depending on whether a coffee cup or a teacup was pushed, I chose to give either a coin or a note as input. This is fine in our setting because you mentioned that we can observe the changes happening to the stack as and when we give inputs to the pushdown automaton, right? But what happens if we cannot observe the stack?
That is an excellent question. As you asked, if you cannot observe the stack and you have to make your decisions independent of how the stack changes, then this problem has been shown to be undecidable.
Oh, wow. Okay. So is this bad news in our setting as well?
Thankfully, in our case, we have some decidability results because viewing the stack gives us some more power. In fact, we are able to show 2 exp time completeness for non-deterministic pushdown automata. And for deterministic pushdown automata, it's even better and we have exp time completeness.
That's great. So how do we get the upper bounds?
We do that as follows. Given a pushdown automaton, we construct an exponentially bigger alternating pushdown system, or APS for short, such that non-emptiness of this APS is equivalent to having a strategy for synchronization in our original pushdown automaton.
Just to confirm, an APS is a pushdown automaton where both existential and universal transitions are allowed, right?
Indeed, that is correct. And we already know that checking non-emptiness of an APS is in exp time.
Right. And so we get the required 2 exp time upper bound for the adaptive synchronization problem, right?
Yes, that is how we get the upper bounds. All that remains is to actually construct the APS given the original pushdown automaton. Let us consider the pushdown automaton, which we have seen as a running example. What we do is a sort of power set construction. And here is how our construction of the APS looks like. The states of this APS are in fact subsets of the states from before. Here, for instance, are some of the states that appear in the APS. Its initial state is the subset containing all 4 states 1, 2, 3, and 4, which corresponds to us not knowing where the token is initially. From this initial state, if we input a coin and the stack is empty, then there are 2 possible options for how the stack changes. We either see a coffee cup or a teacup being pushed. In the former case, we've already seen that we can deduce that the token is at state 3 or 4. And in the latter, the token is either at state 1 or 2. Our alternating system will have a universal transition as shown here, where the pushdown system branches into 2 copies, where one is at the state 3, 4, and the other is at state 1, 2, while modifying the stack as dictated by the transition. That is, when it moves to state 3, 4, it pushes a coffee cup. And when it moves to state 1, 2, it pushes a teacup.
So I see. The states here seem to intuitively correspond to our knowledge of where the token can be in at the moment. And a run of this APS seems to capture a synchronizing strategy for the original Pushdown automaton. What seems to be the case here is that each copy of the Pushdown automaton created during a run, that is created during a universal transition, seems to denote a potential scenario of how the original automaton reacts to our inputs.
Yes, that is correct.
Okay, now that I have seen an intuitive idea behind the construction, let me try to describe a few more transitions. Let's say on inputting a coin, if the stack already contains either a coffee cup or a teacup, then it is popped out, and we have already seen that this does not change our knowledge about the location of the token. Hence, there is a transition that looks like this from the initial state. That is, we have a self loop at the initial state, which pops out either a coffee cup or a teacup when a coin is inputted. Okay. On the other hand, with an empty stack at the initial state, if we input a note, then we once again have two possibilities that could occur. Either a coffee cup or a teacup gets pushed onto the stack. And so we once again have a universal transition similar to the first one that you had described, where the pushdown system branches into two copies. However, this time it branches to the subsets 1, 3 and 2, 4.
This is correct indeed. And this is how the construction is performed. We finally declare the final state to be the singleton set containing that state that we want to synchronize the pushdown automaton in.
Okay, this is great for non-deterministic automata, since you already mentioned to me that synchronizing it is 2exp time hard. And so with this construction, we get a 2exp time completeness for the non-deterministic case. However, if we do the same construction for deterministic pushdown automaton, we only get a 2exp time algorithm. But you mentioned that the problem is exp time complete. So what makes it faster for the deterministic case?
That is a very good question. So in the deterministic case, the APS that we construct has a very special invariant. Along each transition, the total number of states in the subsets is non-increasing. So maybe I will give you an example. The initial state here, for example, is the subset of size 4 because it contains all 4 of the states. Now let us consider this transition that is highlighted. So this transition is a universal one leading to 2 states, each of which has size 2. Hence, the total size of the subsets at the tail end of this transition is 4, which is at most the size of the subset at the head end of the transition.
Right. So because of this invariant, there can be at most n universal transitions in any run of the constructed APS, right? And so any run of this APS can have at most n leaves. Am I correct?
Yes, indeed. Hence, it suffices to solve the following sparse emptiness problem for APS, which is the following. Given an APS and a number k, we want to check whether this APS has an accepting run with at most k leaves.
Okay. And how fast can we solve this?
We can solve this in time n to the power c times k square for some constant c, where n is the size of the given APS and k is the number of leaves.
Okay. With this result, because we construct an exponentially sized APS, which can have at most n leaves in a run, this result gives us an algorithm with running time 2 to the n to the c times n square for the synchronizing problem for the deterministic case. And so the total running time amounts to 2 to the c times n cube, right?
Yes, that is how we get our exp time upper bound for this deterministic case.
Okay, so how do we prove this result for the sparse emptiness problem? it seems to me that since we are only searching for runs with k leaves, we can simply implement a guess and verify procedure.
Oh, we could do that, but the problem is the following. Even though we are looking for runs with k leaves, this does not rule out a long run. That is, a run which is quite deep but not very broad. For instance, the tree illustrated here has only 4 leaves, but it can be arbitrarily long. Hence, it's not easy and quite costly for us to just guess a run.
You are right. But since the tree that we are searching for cannot be very broad, as you just mentioned, it means that if it is rather large, then most vertices in the tree have just a single child. Can we exploit this somehow?
Indeed, we can, and that's what we do. For any accepting run, we extract its skeleton where we only keep the branching nodes and the leaf nodes, and we discard everything else, as shown here. As you mentioned, since most vertices in the tree have just a single child, this skeleton can be substantially smaller than the original run. We can then use classical results on pushdown systems to guess and verify skeletons of runs of an alternating pushdown system. This then gives us the required result.
Okay, that is great. So just to recap our results, we have seen that the adaptive synchronization problem for non-deterministic pushdown automata is 2exp time complete. And for the deterministic case, we have seen that it is exp time complete, and therefore we get an exponential reduction in time complexity when we move from non-determinism to determinism. Finally, as an independent result, we also have that the sparse emptiness problem, that is, the problem of checking if a given APS has a run with at most k leaves, can be solved in time n to the c times k square for some constant c.
Thank you for your attention.
Well, thank you very much. We now have a few minutes for discussion. So I guess everybody just write questions in the chat and on the Q&A. And I guess the authors on the panel could, of course, if they want, ask their questions directly. I have an obvious one to start. What's the implication of all this for visibly pushdown automata?
So that's something that we've not thought of yet. And we had considered looking at extensions of this, and this was in one of our to-do lists.
But is there a conjecture of whether or not it's decidable?
So I think there is some, I think Bala can answer this better. There is some result that has been done on visibly pushed automata, which, 1 minute.
Yeah, I think I'll join it. So okay, since we prove the general result for pushdown automata, so it also holds for visibly pushdown. So because assuming that we can view the stack just like we do in this setting, right? But there are results even so for visibly pushdown automata, there are results on synchronization even without viewing the stack. So even non-adaptively, it's still decidable. So our results imply decidability for visibly pushdown automata, but for as far as complexity is concerned, we don't have any completeness results.
All right, that makes sense. Thank you very much. Yeah, I still don't see questions. So maybe let me ask another one. Is there something you can say about the size of the synchronizers? I mean, I understand they're not bounded, right? But
you mean the strategy to synchronize?
Yes, the strategy of how many states do you need?
So for deterministic case, as we observed, it again can be arbitrarily large, and we even think that it would be exponential given that we have a lower bound. But these are kind of trees that are not very bushy. So they are very sparse trees. So you'll not have too much branching, at least in these strategies. Because if you initially know your intent states, it's a deterministic automata, you can't be in 11 states in the next step. So that's kind of, that stops you from having too large a strategy. But theoretically, I don't think we have a concrete example for this, but you can have, if there are n states, a tree which has height at least n choose n over 2, because that's, you can go through all subsets.
All right, yes.
Of size.
Thanks a lot. Okay, guys, if you have any questions, speak now. Maybe I have one more thing I would like to ask, applications. So in the paper, I think you mentioned virus detection or something like this. Could you elaborate how that works?
Okay, so I mean, we don't exactly have applications of this. So this paper we mentioned this virus detection to motivate the setting of viewing the stack. So and I only read these. I read these papers, but I have not exactly worked in the virus detection area, so I don't exactly know. But I read the papers are cited, and in those papers it's mentioned that there are virus detection programs which examine whether a program is a virus or not by examining the calls made by the program to the OS substance. And then one of those papers, I remember this was in Bacchus some year, 2008 or something. And the idea was that they would model these programs they would abstract these into Pushdown Automata. And then they have a logic which talks about contents viewing across the stack. So they can somehow observe the contents happening to the stack. And then based on this, they have a logic to then try and identify whether a program is a virus or not. And the reason we are, and we also mentioned this in a paper, is that the reason we put this is to somewhat justify our notion of being able to view the stack, but not being able to know where the program location is, because the idea is that we are able to infer something about the control structure while observing something happening to the stack. And this seems to have been also, the setting seems to have been also introduced or studied in a different setting. And we just want to write that to motivate our setting.
All right, very good. Thanks very much. Yes, I think it's time to move to the second talk. So this is about decomposing permutation automata. Igor, if you would roll the tape.
Dear everyone, I'm Nicolas Mazzocchi and I will present the paper Decomposing Permutation Automata, which is a work joined with Petra Wolf and Ismail Yeager. The divide and conquer approach is fundamental in many fields of computer science. This principle consists to tackle a problem by decomposing it into simple parts, such that the solution of the original problem can be deduced from the solution of these parts and how they are combined together. Of course, not every instances can be decomposed. The instances that allows this heuristic are called composites. In this presentation, I will talk about the notion of compositionality for deterministic finite state automata, and I will call them DFAs. For a DFA, compositionality requires the existence of a collection of smaller automata in terms of the number of states, and the invariant that we would like to preserve is the semantics, which is the language denoted by this DFA. In particular, we don't care about the underlying structure of the automaton here. This is an example of DFA. Its language is the set of words that label a run from the initial state here to some final state. There is only one there. In that case, the language contains words with an occurrence of both letters A and B. And as you can see, this DFA can be expressed by the product of two automata. And since each of them have less states, we have here a decomposition. So our initial DFA is composite. Compositionality of DFA find application in hardware engineering, where the design of large-scale DFAs become quickly challenging and less robust. In our example, the compositionality offers a way to keep the collection of small automata even if we ask for more letters to occur. Here, if I had a token like this, the size of my initial automaton grow exponentially faster than the size of my decomposition. Compositionality can be also used in verification as a rewriting heuristic for specification. In fact, those gadgets are all the automata theoretic presentation of the well-known liveness property. And so, the original automaton can be seen as a conjunction of liveness property in this case. It's time for me to be more formal. I will call factor of a DFA an automaton which is smaller in the number of states and coarser, which means that its language is more permissive in the way it accepts words. Then, the k-factor's compositionality of DFA asks whether it exists at most k-factors such that the intersection of the language exactly denotes the original language. Actually, since factors are coarser, one direction of this equality always holds. So this equality can be seen as the preservation of all rejecting behavior of the given DFA. Now the question is, how can we decide whether a given DFA is composite? Concur4 and Jonathan Moyev gave us the following algorithm. Since there are finitely many smaller automata, we can list them, and as a matter of fact, there are at most exponentially many. Then we can filter those that are not coarser in order to deal only with factors. We consider the product of all of them, and as I said before, by coarseness, we have already one direction of the equivalence. So from this product, we can finally check the other direction with some standard procedure and ensure that all rejecting behaviors of our original automaton are preserved. Orna and Jonathan published this X-space upper bound, but also provide an n-of space lower bound. Yet the precise complexity of compositionality is open with this doubly exponential gap. As a side remark, the algorithm is mostly the same when we bound the number of factors with a given parameter k. But the complexity becomes p-space because the size here of the product is bounded polynomially. Our contribution focuses on some subclasses of DFAs, and the main one we will consider is permutation DFA. A permutation automaton is both deterministic and backward deterministic. In particular, this pattern cannot appear in a permutation automaton. Otherwise, some states will be reachable from two distant states, and so that will contradict the backward determinism. We also consider commutative automata that ask the transition function to be confluent. Basically, whatever the order of letter is, a commutative automaton reaches the same state. So again, this pattern is forbidden for commutative automata. In fact, Orna and Jonathan shown seminal results stating that the compositionality can be decided by the use of structural properties. At the beginning of this talk, I said that we do not care about the structure, but it turns out that these subclasses of DFA allow such characterization for compositionality. Our contribution consists to simplify the criteria, inducing a better upper bound for some subclasses. I will not have time to talk about it, but in the paper we also investigate the number of required factors for decomposition. Mind that more factor the decomposition needs, less beneficial it is to consider it, since we may end up with an overall bigger representation compared to the original DFA. Let us start with permutation DFA that are also commutative. In this figure here, we can see an example of commutative permutation Dfa with two letters. I remove the label on the transition by encoding them with dashed line, let's say it's the letter B, and plain line, let's say it's the letter A, to make the picture cleaner. And now I want to introduce you the notion of word iteration. This construction takes a word and iterate it. So let's consider a plain transition as word, for instance, and we start on the initial states. We iterate our plain transition, visiting some states, and eventually reaching back the states in which we started. This actually can be proved as follows. Given a starting state P and a word U, since the number of states is finite, the iteration eventually visits twice the same states, and so the word iteration always has this lasso shape. But remember that the automaton here is a permutation automaton, which means that this pattern is forbidden, and so those two states here and there are the same. By induction, we can prove that the iteration reaches P again eventually. Okay, together with determinism, this property allows us to apply independently the word iteration on states that have not been visited yet. This construction, in turn, partitions the state space in a given of the given Dfa. There is another property that I would like to show. If we have two classes induced by our word iteration, let's consider those two here, and such that we can reach one from the other by reading some word V, whatever. Then, by commutativity, since we can reach these states from this one while reading the word V and then U, we can also do it while reading U and then V by commutativity again. Then by induction, we can prove that all states from the class above can reach some state of the class below. The purpose of this property is that we can actually merge all states that belong to the same class without interfering with the transition relation. And when I say merge, I want to keep witness of the acceptance of the states. That is, the generated states, which is the merge of the whole state of the class, is accepting if and only if there is one accepting state in the considered class. So this one is accepting because there is here one, but here this is not accepting because none of them are accepting. Back to the example, if we merge states with the same color that we construct, we obtain the following automaton. This is a factor since we reduce the number of states by merging some together, and we did it while relaxing the acceptance condition, which ensures the closeness. To summarize, from a word, we are able to construct a factor, but this one in particular is a bit stupid. As you can see, all of its states are actually accepting. So this factor accepts all words, which makes it completely useless in the big intersection of decomposition for the compositionality problem. That's why we consider word covering instead. A word U covers some non-finite states P if the class induced by the word iteration from P is not a singleton. That's ensure that we effectively merge states together. In addition, we ask this class to contain only non-finite states, and this ensures that we actually get at least one rejecting state in the induced factor. The k-factor compositionality for commutative permutation Dfa is then characterized by the fact that every non-finite state can be covered by k words. Back to our example, we can actually choose the following 3 words in order to cover all finite states together. They are actually represented in red. So we conclude that our example was composite, and after merging our classes, we obtain these 3 factors as the decomposition. From our theorem, we can naturally design the following algorithm, which basically checks whether every non-final state can be covered by some words. And in addition, these words can be guessed as the shortest path because our automaton is deterministic. In turn, this allows us to obtain a n-log space algorithm to decide the compositionality for commutative permutation Dfa. In case where the number of factors is fixed, the algorithm is essentially the same, but it differs since we cannot guess the new words for every final state here. We must guess the k words first, and then check whether the guessed words suffice to cover all non-final states. As a consequence, the complexity to decide k factors compositionality is NP. Now, the big question is, can we generalize this word-covering approach? The answer is positive. Let us consider this new example, which is a permutation automaton that is not commutative. It's easy to see that it's not commutative because if I read a plane and then a dash transition, I go from 1 to 2, where if I do the converse, first dashed line and then plane line, well, I reach 4. So this automaton is not commutative. As previously, we are looking for construction that define families of states which are consistent with the transition function. So let's try the subset construction. I start with the set of states 1, 2, 3. This is completely arbitrary from now. I stay in the states while reading plane transition. And if we take a dash transition, we move to the set of states 2, 4, 6, and so on. Note that this subset construction that I just construct here may induce a larger automaton, but luckily this is not the case here. What about the other constants? Well, I just said that the size may explode, so that's something we must check in our algorithm. And for the coarseness, we can ensure it as previously. We define the set of states final if and only if at least one state in the set is final. So those two contain the set 5, which is the only final, and those two contain not the state 5, and so they are not final. For the preservation of rejecting behavior, this is a bit less clear. So consider the state 4 here, which is not final. So every behavior that ends in 4 are rejected. The state 4 can be reached from the initial state 1 by reading 2 plane transition and then 1 dashed transition. The factor that we just construct, this behavior is also rejected. So 2 plane and then 1 dashed is also rejected. Great. But another way to reach the state 4, which is by reading first 1 dash line and then 1 plane line. The factor we construct for this behavior is actually accepted. Dashed line, plane line, and this is an accepted state. So this means that not all rejecting behavior of the state 4 are preserved here by this factor. This is where the magic of permutation Dfa helps. However, Dfa is backward deterministic. And so, since we do have a non-final state, which is this one, we can read backward our problematic behavior, which is dashed and then plane. So we read backward this behavior, and we reach these states here, 1, 5, 6, which could have been issued at the initial states of our factor, since it contains 1. So, to summarize, previously with word covering technique, all rejecting behaviors of non-final states was preserved by a single factor. Now, with a subset construction, all rejecting behaviors of non-final states is preserved by a family of factors obtained just by changing the initial state. Again, the construction that I gave is not completely fine. So here is the notion of set coverage. A set S covers a non-final state P if the number of sets induced from S by reading transition is less than the number of states in the original automaton. In addition, we require that some induced sets contain P and contain only non-final states. This ensures that the factor has at least one non-final state. The compositionality of permutation Dfas is characterized by the fact that every non-final set can be covered by some sets. Note that we don't have the beautiful correspondence k-factors compositionality with k-coverage anymore. And this is since rejecting behaviors of non-final states may involve polynomially many implicit factors now. So from this fact, we can design the following algorithm, which basically check whether every non-final state can be covered by some guessed sets. This gives us an NP algorithm to decide the compositionality for permutation Dfas. In case where the number of factors is fixed by some parameter k, we can use the same trick as before, but we will obtain a p-space algorithm, and this is already a result that we have for the general case. The following table summarizes the result of our paper. I did not provide the proof of NP hardness, which actually relies on large decomposition. Last year, with Orna and Ismael, we provided an infinite family of composite Dfa such that each Dfa requires to be decomposed a logarithmic number of factors with respect to its size. Now, we are able to provide a polynomial lower bound for commutative permutation Dfas. Yet, the family that we exhibit in this paper requires polynomially many factors, but those factors are small enough to keep the size of the decomposition beneficial. So as a future work, it would be interesting to investigate composite Dfa for which all decomposition is larger than the initial number of states. And that's it for me. Thanks for your attention.
All right, thank you very much, Nicolas. Yeah, everyone, please write questions again, either in the Q&A system or on the chat. Maybe, Nicolas, we could get started. Applications. You mentioned verification, right? But could you explain a little bit what properties are expressible as permutation automata? Where would it be most useful?
That's really a good question, but indeed, the way we motivate our work is mainly the model checking, where you have to compute the whole automata for the negation of some formula. And this formula may be big, and then you may construct a very huge automaton, and it's easier to just split it and like run in parallel some model checking algorithms. But it's true that what is actually feasible as a property with permutation automaton is not completely clear to me. And the motivation for permutation automata is in the paper motivated by another argument, which is the fact that for circuits, having both the forward and backward determinism is something that creates more robust circuits because of something that I'm not super expert, but basically, I don't know, the structure make it the circuits is more robust. You can have hardware bugs otherwise.
Mm-hmm.
But in fact, knowing really what kind of property and how interesting are there for model checking it's something that we should have provided maybe.
By the way, for model checking, I guess it would be interesting to have omega automata, right?
Yes.
Would it be easy to generalize to that?
At some point we thought about it. We did not look too much because I think it changed quite a lot the setting. So yeah, also here the determinism play a big role. I don't know whether considering deterministic Decay automaton will make really much sense, since it's even less expressive. So yeah, I don't know.
Mm-hmm, mm-hmm. I guess another point related to that is, I guess you would want to have small automata for that purpose, right?
Yeah.
You only required that they're smaller than the given automaton. But is there such a, I mean, could you require to have a minimal decomposition or something like that?
So it's some question that have been answered but not published by some student of Orna, Moyef, that's work on how large the decomposition can be or how small. And basically the results he got is that, oh, you can focus in having small automata, but you will have a huge number, or having not a lot of automata, but they will be huge. And then this in turn make us think about the notion of compression. So now the problem will be, we want a decomposition such that the sum of all states in this decomposition will be still better than the original automaton. And actually we solve this problem. The compositionality, I mean, the compression will be NP complete then, but it's something we did not really wanted to put in our paper just because it's super technical, and I think the paper is already a bit technical.
I see. So just to understand, this is the question whether you can compress it beyond a certain bound?
Not a bound. Well, the bound is the number of states of the automaton. So you ask.
Oh, it's the given automaton. That is okay.
With the number of states of the automaton, can I create a collection of automata such that I realize the same language, but it's composite?
And could I replace this bound with another bound? I mean, if I ask if I can do it with half the states.
The bound is fixed, then the problem becomes simpler theoretically, in the sense that finding hardness is easier when you fix the bound on the number of states. Here, so far, we don't have really lower bound hardness for the general case. We only have the NP completeness when we fix the number of factors. But if we fix, if we don't fix anything, the hardness is n of space, which is quite ridiculous still. But this seems to be connected with the prime numbers and number theory. So I think the hardness the result is very hard to get. So that's justify why we don't have that.
All right, thank you very much, Nicolas. Any other questions for this paper? Apparently not. Well then, let me thank the authors of both papers. It was a very interesting session. We started a little bit late, so I think it's fine that we also finish a little bit late. I guess we now have 10 minutes of coffee break, and then at 6:05, there's the Test of Time award session. Thanks, everyone.
One thing about the test of time, it would be on the keynote keynote Zoom session. You'll go there to see the test of time. Thanks for everybody again.
Right. Bye-bye.